next lecture, I would like to invite Mr. Christopher Schmatz to present his paper entitled Effect of Crack Opening Velocity on the fracture behavior of hypostatic semi-structural threading when subjected to more bound.
Okay, thank you for your kind introduction. Today I want to talk about hyperelastic adhesives, and especially this is an adhesive which is very stiff and very tough, and we are looking how the fracture behavior is influenced if we change the crack opening velocity or the loading rate. And we want to look for mode 1 loading, so we're dealing with Dcb tests here. I will start with a motivation and go on with the Dcb test setup. I will show you the evaluation methods which were used to evaluate the experimental data. I will show you the results and give you some impressions how the fracture behavior changes by rate when we are looking at videos taken from the side of the specimen. And I will close this presentation by giving you a summary and an outlook. Okay, let me first mention that hyperelastic adhesives, they provide some important advantages compared to epoxies. If you think about car manufacturers, hyperelastic adhesives, they provide a higher energy consumption if the adhesive bond line is in impact. And hyperelastic adhesives, they have higher fatigue resistance and consequently better damping properties compared to epoxies. So due to their low stiffness, the normal application case of hyperelastic adhesives, they are non-structural. Think about windshield bonding, those blue bond lines here. These are non-structural bond lines. But there are structural applications as well. For instance, look at those yellow bond lines here. These are bond lines which bond the main body of a car, and the adhesive we are looking at is, for instance, used at BMW electronic models to bond the aluminum chassis to the live module, which is made of carbon fiber reinforced plastics. So keep in mind that there are structural applications for hyperelastic adhesives as well. And due to the viscoelastic material behavior, the fracture behavior is influenced, amongst other things, by rate. And the manufacturers, they need simulation tools that can predict this failure of those connections, which depends on rate. So this is the Dcb test. We used Sikaflex ultra high modulus, and this means that the elastic modulus is relatively high for a hyperelastic adhesive. We used it in conjunction with Sika Primer 207, and the adherents, which you can see here, they're made of an aluminum alloy, and the cohesive layer thickness was constant 3 millimeters. So how the Dcb test works, you have this tensile loading on the left side, and the adhesive layer, it is introduced a peel loading in the adhesive layer. And we measure, besides F, the rotation of the force introduction points, named as theta here, and we measure at the position of the pre-crack, the crack opening displacement, which is denoted by U here. The pre-crack was introduced by razor blade. So this is the test setup. You see the Dcb specimen here. And these clamping devices, they were used to ensure that the force introduction points can rotate around those axes here. And we used the rotary encoders to measure theta. Load cell is placed up here. You can see it in this picture, but you see some measuring flags which were used to measure the crack opening displacement optically by line sensor system. So this line sensor detects variations in contrast between the white measuring flags and the black background, and this is where you get the crack opening displacement from. We used another camera system on the right side, which is focused on the edge of the specimen to get pictures made from the side to observe fracture behavior. So how was the evaluation done? We calculated J directly from the measured values F and theta by using this approach as proposed by Anthony and Paris 1988. B is the out-of-plane width of the specimen, and the fracture energy J critical was set as maximum of measured J. And this is the first parameter regarding the cohesive law. And the cohesive law we calculated by applying the bar and blood ductile crack model by the first derivative of J with respect to crack opening displacement, and the second cohesive law parameter, the strength sigma 0, was calculated by averaging over the resulting sigma plateau. So this is the last parameter, the cohesive stiffness K. It was calculated by second derivative, and we averaged here within the initial region. Okay, let's have a look at measured curves. You see here J over crack opening displacement and the corresponding first derivative as the traction separation law. The tensile testing machine was controlled regarding these tests on constant crack opening velocity. So traverse, or the crosshead, was moving in a way that the resulting crack opening velocity is constant. If crack opening velocity is increased now, you see that the maximum value of J is rising. So fracture energy is rising with rate. This is an expected result. And if you look now at the traction separation laws, they look trilinear, trapezoidal, but the initial portion which we used to calculate the stiffness seems to be nearly unaffected by rate. But the cohesive strength as the plateau stress is rising as well as the fracture energy. So two of the cohesive law parameters are dependent on rate, and stiffness seems to be not dependent, although we have viscoelastic material behavior. This is now the fracture energy, and we have here all tests done. So these are 12 tests, 3 per one crack opening displacement. And you see that fracture energy seems to plateau over this crack opening velocity. So we use this analytical approach to describe the fracture energy over the actual crack opening velocity. This approach has a lower bound here, which is physically sensible if you think about that fracture energy must not fall below 0 for the quasi-static limit case, but we can say this plateau is not really convincing, but we've chosen to think about this plateau as sensible. And we've seen a plateau for higher rates. So J quasi-static is the lower plateau, and this is a fitting parameter where this curve here changes its curvature. And another parameter which is rate dependent was the cohesive strength. Another approach here, and again we have a lower plateau. This is a parameter giving you the slope of this curve here, and this is the quasi-static test speed this quasi-static test speed or crack opening velocity. And as I said before, we've seen no dependence of stiffness on crack opening velocity, so we assumed here stiffness to be constant. We have large scatter, I think, but it was not possible here to create a convincing dependency. So we have now the traction separation law together, which is rate dependent. And we are changing now the controlling of the testing machine from controlling on crack opening velocity to controlling, that you all know, on constant crosshead speeds. You see J over time, different test speeds, and now the curves of J are plotted until the specimen is completely damaged. So you see here the fracture behavior. And the fracture behavior is unstable. So we have here stick-slip cracking, and this effect of stick-slip fracture is really the oscillations are very high in this region of test speeds. So we take now out this curve here to look with the pictures made from the side what's happening. Picture 1, you see the pre-crack gets visible, and at picture 2, distinctive necking and blunting of the crack tip appears. We have an hyperelastic material, and from the picture 2 to picture 3, crack propagation starts. And this is unexpected that we have crack propagation before reaching the fracture energy, before we reach the maximum value, but we've seen, colored in blue here, subcritical growth. And at the point of maximum J, crack is jumping. So crack propagation gets overcritical. This is what you see with this falling region here. And at picture 4, crack propagation changes again from overcritical to subcritical, anew. We are looking now at videos which were made from the side. You see the lowest test speed driven at 2 microns per second. You see a curve J over time. Crack tip gets visible now. And please look at the crack tip. Maybe you see it. We have subcritical crack growing before reaching maximum J. Now we reach the fracture energy and we have a crack jump. And after this crack jump, crack propagates nearly stable anew. We have no sawtooth shape here. And if we look now at the fracture patterns, you see here a very flat area. This was by inserting the razor blade. And this rough area here is subcritical crack growing from this point to this point. And then crack jumps and the fracture is near the interface, which is commonly observed regarding very slow test speeds. We are increasing the test speed. You see again J over time. Pre-crack gets visible. And distinctive blunting appears. Crack tip is necking. And now we had a marginally subcritical crack growth again. And we're at the point of maximum J. The crack propagation turns now over to overcritical, but this appears here many times. So we have here distinctive stick-slip fracture. Okay. So by changing of crack propagation rate, you see it in this curve here, but if we look at the fracture patterns, you see it in the fracture patterns as well. First, flat region by inserting razor blade. This is the first subcritical crack growth. And then you see a flatter region, which means that the crack jumps here. And then we have here a rougher region again, subcritical crack growth, and it jumps, and this is repeated here. So you see these rest lines here, or these are not rest lines, but these are areas of sub and overcritical crack growing. And now we're increasing test speed again, 10 millimeters per second. You see J over time again, and the specimen here. And necking and blunting appears. Maximum J, we have 1 overcritical crack jump, and stick-slip fracture disappears. So it's just between some regions of crosshead speeds that we have distinctive stick-slip fracture, and we see no rest lines anymore, or no changing in rough and flat regions in the fracture patterns. So to conclude this, we've investigated effective loading rate on the fracture behavior of very tough and stiff hyperelastic adhesive joint. We've seen these analytical functions to describe the rate-dependent cohesive law. Fracture energy and cohesive strength increased, and we had this plateau region for higher range on fracture energy. And the stiffness stayed nearly constant, or was assumed to be constant. We changed controlling of testing machine, looking at the fracture behavior, and we've seen unaffected by rate in every case. We had subcritical crack growth before reaching maximum J, and this turns over to overcritical in a certain range of these velocities. We had this stick-slip fracture, these alternating effects. And in future works, we are focusing on a cohesive zone model that can predict these effects here of stick-slip fracture. If you have some questions, please contact us at the conference or later, and thank you for attending the presentation.